So now we're back to Kaggle's Intro to Machine Learning, Underfitting and Overfitting. We're going to fine tune our model for better performance. All right, so let's get to it. So at the end of this step, we're going to understand the concepts of underfitting and overfitting. And we will be able to apply these ideas to make our models more accurate. I can attest. All right, so experimenting with different models. Pardon me. Now that we have a reliable way to measure model accuracy, we can experiment with alternative models and see which gives the best predictions. But what alternatives do we have for models? Good question. We can see in scikit-learn's documentation. Let's open this up real quick. There it is. We can see in scikit-learn's documentation that the decision tree model has many options. Yes, there are a lot of different parameters we can throw into this thing, or arguments, I should say. Where are we? Oh, right here. Has a lot of different options, more than we'll want or need for a long time. Yes, true. Very, very true. The most important options determine the tree's depth. We're going to recall from the first lesson in this course that a tree's depth is a measure of how many splits it makes before coming to a prediction. This is a relatively shallow tree right here. So this is the same one as the one we saw on the first lesson. Does it have more than 2 bedrooms? If not, is it larger than this? If not, this is the price. If so, it's this. And if so on this one, if not on this one, this is the price. If so on this one, this is the price, all right? So yeah, basically. So in practice, it's not uncommon for a tree to have 10 splits between the top level, all houses, and a leaf. I believe it. As the tree gets deeper, the data set gets sliced up into leaves with fewer houses. True. If a tree only has one split, or only had one split, it divides the data into 2 groups. True. If each group is split again, we would get 4 groups of houses. True. So 1, 2, we got 4 here. And then if we split this up, we'd have 8, right? Splitting each house would create 8 groups. And then we keep going until it's 2 to the 10. And we would get 124 leaves. All right. Just simple, what do you call that? Exponential, whatever, by 2, whatever. I don't remember what it's called. Anyway. When we divide the houses among many leaves, we also have fewer houses in each leaf. True. Leaves with very few houses will make predictions that are quite close to those homes' actual values. I mean, that's true if you're predicting... What? Oh, it'll make predictions that are quite close to the homes in the training data's actual values, right? But they may make very unreliable predictions for new data. And that's the only reason we would make a prediction would be for new data, because why would we make a prediction for stuff we already have? You're not really predicting anything, right? Because each prediction is based only on a few houses, all right? So that's why it would be unreliable, because instead of like having 10 million things in your training data, you got like 6. You know, how are you going to guess with 6? How's a computer going to guess with 6 examples of what could happen? You know? Not possible, or at least very, very hard. All right, so this is a phenomenon called overfitting, right? When there's too many leaves, where the model matches the training data almost perfectly, but does poorly in validation and other new data. True. On the flip side, if we make our tree very shallow, it doesn't divide up the houses into very distinct groups. True. I guess it would be like if we just tried to make a prediction on only 2 or more bedrooms, you know, if like, okay, so it has 2 bedrooms, you know, but you know, this one place has a pool and a helipad, and the other place has, you know, a broken driveway. They're not going to be the same price, right? Of course not. All right. So let's go. On the flip side, blah, blah, blah. So at an extreme, if a tree divides houses into only 2 or 4, each group still has a wide variety of houses. True. Resulting predictions may be far off for most houses. Also true, even in the training data. And it will be bad in validation too for the same reason. I guess that's why when we did that thing in the last video, it had the training data like off by like 400 instead of like off by 0, because it's still, you know, it's still not giving a perfect prediction. Whatever. All right. So when a model fails to capture important distinctions and patterns in the data, true, so it performs poorly even in the training data, this is called underfitting. So if there's not enough leaves, it's going to be underfitting. Okay. So since we care about accuracy on new data, which we estimate from our validation data, we want to find the sweet spot between underfitting and overfitting. Visually, we want the low point of the red validation curve in the figure below, right? So when we underfit, when we add more leaves, tree depths, when you add more leaves or depth, it'll start, what is this? I guess this is way off. I guess this is what looks like way off. It'll start getting closer and closer to reality, or at least a good prediction, and then it'll hit a sweet spot right here, and then after that it'll start going up again because it's starting to overfit. All right, so let's go down here with the example. So there are a few alternatives for controlling tree depth, okay, and many allow for some roots through the tree to have greater depth than other roots. We'll take your word for it. All right, but the max leave the nodes argument provides a very sensible way to control overfitting versus underfitting, right? So when they're saying this, they're talking about this right here. Max leaf nodes, by default, it equals none, but we can change that anytime we feel like it, all right? The more leaves we allow the model to make, the more we move from the underfitting area in the above graph to the overfitting area. True. So this would be like one max leaf node. This would be like 100 max leaf nodes, and this would be like 10,000 max leaf nodes, or something like that. We'll get into that in a little bit. We can use a utility function to help compare MAE scores from different values for max leaf nodes. All right, so we're going to make this utility function right here, where we import mean absolute error and the decision tree regressor, and then we make this get may what do they call it, utility function, and we're going to have max leaf nodes in there. And this one is going to be inputted into this. All right, we're going to find that somewhere else, and then we're also going to have the train X, the val X, the train Y, and the val Y. Right, and we're going to make that too in a little bit. And then after that, so the first part of this, what is this thing called? Of this function, we're going to have a decision tree regressor, and we're going to put max leaf nodes equals max leaf nodes. Right. So remember, max leaf nodes to start equals none. So we're making this equal this, which is this that we're putting in there, right? And then we're going to have random state equals 0 as usual. So now we're going to fit and we're going to save that to a model, right? So now we're going to fit this model with train X and train Y. And then we're going to do a prediction right here. So model.predict. So this model dot predict, and then we're going to put val X in there. And then we're going to say the may is the mean absolute error, what is that thing called, function, and we're getting val y, this val y here, and then putting preds val, which is this right here, and then we're going to return this, which is this. All right, basically easy stuff, and we didn't have to think about it. You know what I mean? Somebody graciously thought about this for us and gave it to us, right? So the data is loaded into train X, val X, train Y, val Y, using the code we've already seen. So it's this stuff right here where we import pandas, we do the file path, we read it in, we filter it out by doing the drop nah, we have the price, what is that thing called? Not the data frame. We got the price series, we have the names for the features, and then we're making the data frame based on these names. All right, and that's going to be X, and then we do the train test split, and we've got the train X, train X, val X, train Y, val Y. the same ones we're going to be using inside of this one. All right. So that's where these are coming from that we're going to plug into this. All right. And then there's that. So we can use a for loop to compare the accuracy of models built with different values for max leaf nodes. All right. So we're going to compare the MAE with different values of max leaf nodes. So now we're going to say for max leaf nodes in this, what do we call it in Python? For this list with 5, 50, 500, and 5,000, right? So these are going to be the different max leaf nodes. Remember, we're going to plug these into here when we call this thing right here, this thing, that thing being this thing, right? Of course. When we call this thing, we're going to plug in max leaf nodes, which is going to be first 5, then it'll be 50, then in the next iteration 500, then in the next iteration 5,000, right? And then we're also going to put in train X, val X, train Y, right? And val Y into there too, because we've got all those. And then we're going to print max leaf nodes is going to be the first digit in this thing, which is going to be the max leaf, which is going to be whatever this is. So 5 first, 50, 500, then 5,000. And then we're going to do a couple of tabs, and we'll say mean absolute error is the second digit, which is going to be the my-may, which is going to be whatever comes out when we do the for loop, right? And so when we run this thing, we'll get max leaf nodes, right? We'll get max leaf nodes 5, which is this right here first, and then 50, and then 500, and then 5,000, and then 2 tabs, 1, 2, 1, 1, 2. There we go. And we'll have the mean absolute error string right here, and we'll have whatever the my-may is, and we can see it starts off at 347,000, goes down to 258,000. Then it goes down to 243,000. Then it starts climbing again to even above what it was at 50. So judging on this, somewhere between 5 and 5,000, 50 and 5,000 is where the actual sweet spot to this model is. And I mean, we could put, I guess it's good to start with these big, what do you call it when you do a 10, when you go by 10, when you say order of I don't remember what it's called. Order of magnitude, right? So we start with 50, and then we know it's in between here and here. So on the next run, we can just say between 5 and 5,000. And that's generous, right? We can say run this thing between between 50 and 5,000. So every number between 50 and 5,000, run this thing again, and then we can zero in on the exact sweet spot like that. Hopefully that makes sense to you guys. So of the options listed in this, 500 is the optimal number of leaps because this is the lowest number, right? Of course. So here's the conclusion. Here's the takeaway. Models can suffer from either overfitting, capturing spurious. Let's get this out real quick. Hold on. Spurious. I had to look this up too. Spurious definition. Not being what it purports to be, false or fake. Okay, so capturing fake patterns. The overfitting will capture fake patterns that won't recur in the future, leading to less accurate predictions. Or underfitting, which is failing to capture relevant patterns, again leading to less accurate predictions. So yeah, we're just trying to find the sweet spot here. So we use validation data, which isn't used in model training, of course, to measure a candidate model's accuracy. That's the whole point of the validation data, right? And this lets us try many candidate models and keep the best one. And that's what we would do. We would just keep on searching until we get the lowest number or whatever number we specifically need to find. Maybe the highest number, maybe the lowest number. Who knows? So let's go. Let's go to the next one. I said, let's go to the next one. There we go. Oh, give it a second. All right. So now we're on to exercising. Come on. Exercise, underfitting, and overfitting. And we'll see you next time.